In the year 1915, Albert Einstein published the general theory of relativity. This was undoubtedly the grandest scientific achievement of the 20th century. But like Oliver Twist, Einstein wanted more. He envisaged a powerful framework that would unify space, time, as well as the different forces of nature. And he spent at least 30 years of his lifetime pursuing it. But unfortunately, he failed at it. Several decades later, scientists believed that there might be a way to unify all of these elements in the exact way that Einstein wanted it through string theory. In today's video, we'll take an in-depth look at what string theory is and the latest developments around it. Before we get into the nitty-gritty of today's discussion, let's address the elephant in the room by answering the question, what is string theory? In simple terms, string theory is an idea that attempts to unify the two main pillars of 20th century physics, namely Albert Einstein's theory of relativity and quantum mechanics. The expectation is that, if fully understood, this brain-wrecking theory will provide a robust framework that can explain all of physical reality. But how does it intend to do this? In string theory, it is assumed that reality is made up of infinitesimal vibrating strings, much smaller than atoms, electrons, and quarks. As these strings vibrate, twist, and fold, they create effects in many tiny dimensions that humans interpret as different things, ranging from particle physics to large-scale phenomena like gravity. Although the concept of string theory is largely built around hypotheses, we could still explain it using real-life entities. Imagine you've got a big apple, and you're asked to find out what exactly makes up the apple. What would you do? In this situation, most people will list out all the nutritional content in the apple. But that's not the way things work in physics. Instead, you want to look deep into the apple to find out what its true component is. And to do this, you'll need to magnify it, perhaps multiple times until you can find its molecules. Of course, molecules are not the end of your search because they themselves contain smaller particles. So, going through the same process that led to the discovery of molecules, if you magnify and enlarge them enough, you'll find atoms. But again, atoms are not the end of your search because somewhere in the deepest part of atoms, around the nucleus, you'll find electrons. Interestingly, the nucleus itself is a product of other particles. So, if you magically pick up a nucleus and magnify it extensively, you'll find neutrons and protons. But what if you decide to take things one step further and magnify the neutrons? Will you find anything useful? Of course you will. You'll find tiny particles called quarks. Normally, this is where we stop to magnify and enlarge particles in search of other particles because, according to conventional physics, this quark is the smallest unit in which a particle can exist. In fact, quarks are believed to be point-like entities with zero size, and most scientists say they are invisible. But string theory disagrees. As disruptive as it sounds, string theory suggests that quarks contain other much smaller particles. So let's say you pick up a quark and magnify it. Conventional ideas suggest you will find nothing. But according to the thesis of string theory, you should find a tiny filament or string of energy inside of it. Just like the strings in a guitar, this string vibrates when it is plucked. But rather than creating musical notes, they produce the particles themselves. Following this line of thinking, we can define a quark as a string vibrating in one pattern. Similarly, an electron would be a string vibrating in a different pattern. Right now, this idea remains a speculation, but if eventually it is proven, it means your apple and any other matter at all are made up of tiny strings vibrating in different patterns. This is the most basic explanation of string theory. But of course, it has quite a long history that dates back to the 1990s. According to a report by the University of Oxford and the British Royal Society, strings were used to model data generated from the subatomic colliders in Europe between the 1960s and 1970s. More importantly, they provided a dynamic way of mathematically describing the strong force, which is one of the four fundamental forces in the universe and holds together atomic nuclei. However, discussions around string theory were minimal until 1984, when two theoretical physicists, Michael Green and John Swartz, discovered equations that showed how strings sidestepped some of the inconsistencies around models that describe particles as point-like objects. The scientific adventure by Green and Swartz produced 5 different theories that explain how one-dimensional strings oscillated in a 10-dimensional reality. About a decade later, a second revolution happened following the 1995 String Theory Conference at the University of Southern California. At this highly intellectual meeting, it was agreed that these different ideas were in fact related and could be unified through another theory called supergravity, which worked in 11 dimensions. Especially because it behaved in a particular situation like Einstein's space and time-bending theories of relativity, it fits Newton's description of objects moving at normal speed. This gave birth to the M-theory, which is one of the spin-offs of the string theory itself. Theorists suggest that M is most likely inspired by higher dimensional objects called membranes. However, since there are no concrete mathematical equations to support it, the M symbol remains a placeholder with no official meaning. However, the belief that it exists gave scientists the understanding and confidence required to develop mathematical techniques for the 5 versions of string theory, and more importantly, how they can apply them in the context where each theory works. Ordinarily, strings are far too small to be detected, even by the most advanced technology. But scholars have been able to theoretically prove their existence at different times. One of such occasions was in 1966, when a description of black hole entropy was published in the journal Physics Letters. For the uninitiated, entropy is the number of ways that you can arrange the parts of a system. But since we can't peek into the impenetrable depths of a black hole, we don't know what type of particles might lie inside or what arrangements they can take. But sometime in the 1970s, Stephen Hawking, with some other brilliant minds, used the laws of thermodynamics and quantum mechanics to calculate entropy inside a black hole. This suggests that black holes have some sort of internal structure that we don't exactly understand. Consequently, all attempts to explore the makeup of black holes have failed, but string theory might be able to give us a spot-on count. In the real sense of things, string theory is not perfect. It's still only a hypothesis, and most of its predictions cannot be proven even with current technology. But so far, it's the only thesis that produces an impossible number of ways to fold up the extra 6 dimensions. From hindsight, every option it provides seems to fit the wide features of the standard model which govern particle physics. But there's barely a way to differentiate which one is the right one. During the 11th annual Isaac Asimov Memorial Debate at the American Museum of Natural History, scholars embarked on an extensive discussion around string theory and whether or not it made sense to endorse it as a viable description of reality. Director of the museum's Hayden Planetarium, Neil deGrasse Tyson, was particularly vocal in questioning the validity of string theory. "Are you chasing a ghost, or is the collection of you just too stupid to figure this out?" he asked. The famous American astrophysicist also added that the progress around the concept has been subpar in previous years, and he isn't far from the truth. Ironically, the main challenge that string theory faces is created by the framework of the theory itself, particularly in the way that it predicts the potential existence of a vast number of unique universes, as many as 10 raised to the power of 500. Such hypotheses provide scientists with a whole puzzle to solve and probably someday explore. But first, they'd have to find a way to prove string theory in real life.